I'm going to start off with opening up this project here on the left. I'm going to change the structure of my folder. First, I'm going to place my cursor on top of Go Blockchain and right-click, then go to New, then Directory. I want to move the code that I have now to a new directory called Block. Next, I'm going to create another folder, so I'll create a new directory and name it as Wallet. And then click on OK. This is going to be a folder for creating the wallet. We have blockchain.go folder, and I'm going to move this to the block folder. And I'm going to next click on OK. Now we see that inside our block folder, we see our blockchain.go. Let's scroll all the way to the top here. Our package name here automatically got updated, and now it says block. Previously, it was main. Since this code is a part of the block package now, we're going to scroll all the way to the bottom and refer to this main function. We aren't going to be using this section of our code, so we'll go to the Go Blockchain folder and create a new Go file. We'll name it main. For our main.go, this package is at the top, so we'll change this to main. Now let's go back to our blockchain.go. We'll copy this and delete it. Then we'll take that code to our main.go folder. When we copy this, Golang will automatically import the necessary package, so we get this. We want to call main and wallet from our main, so we'll delete this. This is how main.go will look once these steps have been completed. Once we've gotten to this point, we want to create our wallet. We'll right-click on Wallet, go to New, then New Go file. We'll name this as Wallet, and click OK. From now, we'll write the codes for our wallet. First, we'll declare the type. We'll write wallet, then struct. Then first, we'll write private key. This is ECDSA's private key. We're doing this because we want to keep the pointer. And we wrote this so this import has been automatically updated. And here we have import crypto/ECDSA. We'll repeat this for public key now. We'll change this to public and do the same for this section as well. Then we'll write func with our name being new wallet. We'll return the wallet pointer. That's going to be our function. And now let's create a wallet and say new wallet. At this point, we want to create our private key, and for this, let's refer to our document. Let me pull up the document right now on the screen. And this is the document for import crypto/ECDSA. Here we have example. So let's click on this, and this example isn't that easy to understand, but hopefully you'll get a general idea of the flow. Now let's bring back our visual for authentication and refer back and forth between these resources. As you see here, first we have ECDSA and our method generate key. We're passing in elliptic P256. This P256 is this point on the bottom here. And we have our reader for CryptoRand. We're putting this in and generating our private key. When we do that, our private key is generated, and this private key is generated as a pair with our public key. So let's refer to our private key. When we look below, we see type private key, and let's look at the details for type private key. We see inside our type private key struct, public key is included. Let's look at what's written for our public key. And this is the content of our type public key. Elliptic curve and the x and y coordinates are mentioned. This simply means that we refer to the x and y coordinates for our public key. This is a little complicated, so we'll refer to this example and work on this step by step. We have ECDSA generate key here, and let's review this method. Let me scroll down. Generate key is this section, and it's saying to put rand IO reader here, and the algorithm for elliptic curve here. We'll follow what it says. And that's how we generate our private key. We'll do error handling here, and for example, let's say our message is hello world. First, we made this hello world into a hash. Imagine that this hash is this transaction. And now let's refer back to our document. We're signing with ECDSA sign here. When we sign, we have our to the right, our private key, and our transaction. We need to use both of these to sign. And when we do sign, we have placed here our reader and also our private key and hash. We have R right here, which refers to this R to the right here, and S here. We return these two values. S is a value that's calculated by using R. So think of R and S as a pair. Think of these as a pair for our signature. And this concept involves complex mathematics, so for now we see R and S here. Don't try to get into the mathematics for R and S, but remember that these values are what makes up the signature. With these values, we're able to generate our signature. And we have our signature, hash, and public key information. Let's say we pass in these three pieces of information to our blockchain node. Our blockchain node needs to be authenticated, and for that, it's these two last lines here. So how do we actually verify? We have our public key that's connected to our dot for private key. We take this public key, hash, and our signature. We take all of these and verify if all of it is valid. We're confirming if it's correct by referring to these three pieces of information. And let's confirm whether this code works by running it. Our signature is this. What's printed here is from this FMT. Then we have signature verified true. For example, let's say we have someone who wants to hack into this. Our hacker is going to rewrite the content for a transaction. For example, let's say the hacker writes hash SHA-256 sum 256. Then for our value, $1 million. So this person is going to try to send $1 million to himself. After that, the code is going to try to verify the hash. We'll run our code, and when we do, we get the result signature verified false. To sum it up, even if someone tries to manipulate our code by rewriting it at this stage, the blockchain node will be able to detect this manipulation. Authentication involves public key, private key, and ESDSA. With all of this in mind, let's get to writing our code. First, we'll say private key, and we want to generate this, but for this, we're not going to do any error handling and keep on going. We'll write ECDSA generate key, then elliptic P256, and pass in our rand reader to create our private key. These two lines are automatically imported here. Now onto our wallet, which is W, private key. We'll connect that to our private key that we just created. Then for our W.public key, this is a pointer, and it was connected as a pair, so we refer to this as W.private key, public key. Then all we have to do is say return W and return our wallet. Right now we have private key in lowercase letters. We want to be able to pull out the public and private key from our wallet, so let's add on a method like a property. For this, we'll say wallet, then followed by private key. And to do this, we'll add on ECDSA private key, which will then be followed by return W private key. Down below, we'll repeat the code with func W wallet. Then here, we want to refer to the string in our private key later on. Let's right now refer back to what's written for private key. This section itself is a struct. What we have here inside our struct, we'll take this private key and want it to be reflected as a string. Let's go back to our code, and we'll add on private key str and return fmt sprintf. We want to show this as a hexadecimal numeral again, so we'll refer to the private key that's stored within this and take the bytes and return. We'll get into more details about this later on. We'll repeat the same process for our public key. We'll copy our code for the private key and replace the words from public key to private key now. Then after we're done with that, down below, we want to return a string from our public key. So we'll replace this to public key str. Then, regarding this return, we include 2% x's. I'm going to delete this section right now, and if you recall, we had public key x and y. Let me explain a little further by looking into public key. when we look inside public key, we see this. We have x, y, and big integer written here. We have x and y coordinates right now. This is what our structure is, and first we take our x bytes, then public key y bytes. We're going to be returning in a format that can be easily understood by us. So we just created our private key and public key for this section. Now let's call this from our main. We'll access our main.go, and if accessing the project like so isn't your preferred style, you could also access main.go from the left side under projects. We want to create our wallet from our main. To do this, we'll say wallet, new wallet, then fmt println, and have our w private key str that we just created to be printed here. Next will be our public key, so we'll write public key and select the str and not byte. Let's run our code with this, and when we run our code, we see that our private key str is printed like so, and our public key str is printed like so. How it's printed is written in a way that can be easily understood by us. If we decide to print in a different way, in other words, if we remove str and then print, we get the contents of our struct and it's impossible to tell what's being done. That's why we created private and public key str. Now let's move on to our next lecture.